Hey everybody, it's Mrs. Harbin. Video notes 9-4. One objective, 4 practice problems. Let's get busy, alright? So, here's what we got to do. KSP. You might be wondering what KSP means. It's the constant of the solubility product. Solubility product constant. Okay. Every solution with the precipitate is saturated because it's got the most solid dissolved of that precipitate, and then the rest is the solid. So if we mix barium chloride and sodium sulfate, we're going to get barium sulfate and sodium chloride, but these are still ions. These are ions, and these are ions. All right. So the net ionic equation is the barium and the sulfate make the barium and sulfate make barium sulfate. So since barium sulfate is a precipitate, it's forming a saturated solution. And so if you think about it this way, the solid is actually dissolving as much as it can, and then not the rest, and that's why it's precipitating. So here's the dissolving equation. So every dissolving equation has what we call a constant for solubility, and it's called the solubility product constant. And you take the things that are aqueous, and that's the barium and the sulfate ions, and you multiply their concentration. So the concentration of barium ions times the concentration of sulfate ions equals the KSP, or the constant for that compound, solubility product constant. But wait, if there's coefficients for the ions, then you have to use those as exponents. So here's another dissolving equation. The calcium phosphate dissolves into calcium ions and phosphate ions, so we need to write a KSP expression. So we take the concentration of the calcium ions times the concentration of the phosphate ions, and this coefficient becomes the exponent for calcium, and this coefficient becomes the exponent for phosphate. So this calculation, if we knew those concentrations, would provide us the KSP for calcium phosphate. Okay? Oh, there it came in. Yay, I did that. I'll write that so you can see it. Alright? So why are there exponents? Because they're coefficients. Alright? Okay, so you try. Write the dissolving equation and KSP expression for lead 2 phosphate. Lead 2 phosphate. Oh, pause it, try it, and then check. PB plus 2, PO4 minus 3. So we need 3 of those and 2 of those for the solid. So it's going to dissolve into 3 lead, 2 ions, and 2 phosphate ions. So what's the KSP expression? Well, KSP is going to equal the concentration of the lead, because it's aqueous, times the concentration of the phosphate, because it's also aqueous, but because there's 3 times as many ions of lead, then there's exponent of 3, okay? And there's an exponent of 2 for the phosphate. Okay, so this is what's called the KSP, or the solubility constant expression. So we can solve for either find this, or find this. You can solve for any part of it because we know what molarity means. So calculate the solubility product constant. So find the KSP for lead 2 chloride. If you have 50 milliliters of a saturated solution, and that 50 milliliters had 0.2207 grams of lead chloride dissolved in it. Okay, so let's write the dissolving equation. PbCl2 is the solid, dissolves into lead ions and 2 chloride ions. KSP expression, KSP, is going to equal concentration of lead ions times the concentration of chloride ions, and because there's a 2 there, we got to square that. Okay, we're trying to find this, so we have to plug in the concentration of lead and the concentration of chloride. But we don't know that yet because we have to calculate it. So this is grams and this is milliliters, but in order to get molarity or concentration, we need moles per liter. So I'm going to take the 0.2207 grams of lead chloride and change it into moles. So I go to periodic table, I get 278.10 grams of lead chloride for every 1 mole of lead chloride, and I get 7.9 times 10 to the negative 4th moles. All right, and that's moles of lead chloride. All right, but what do I need to plug in here? I need to plug in the concentration of lead ions and the concentration of chloride ions. Well, here's what I want you to realize. If this much lead chloride goes in and it saturates the solution, then the concentration of the lead chloride would be 7.9 times 10 to the negative 4th divided by 0.050 liters, because I need molarity, and that gives me 0.0158 molar of lead 2 chloride. But what happened to that lead 2 chloride? It all dissolved. So that means I have 0.01558 molar lead ions when all of this lead chloride dissolves. And then I have 2 times as much chloride ions, because I get 2 for every lead chloride that dissolves. So now I have to plug this into here and this into here. So the KSP is going to be equal to the concentration of lead, 0.0158, times the concentration of chloride. And the concentration of chloride is 2 times 0.05, and then you guys square that. Okay, so I plug that into the calculator, and I get 1.58 times 10 to the negative 5th. And so that is the constant for the solubility of lead 2 chloride. Right? So I solved for KSP because I know what happens to solutions and I know what molarity means. Woohoo! All right, can we do something else? This one says, what is the concentration of barium ions in a saturated solution of barium sulfate? What are we trying to find? We're trying to find the concentration of barium ions. All right, what do we have? We have a saturated solution of barium sulfate. So here's BaSO4, barium sulfate. It's going to dissolve into barium ions and sulfate ions. All right, so what is the KSP? KSP is going to be equal to the concentration of barium ions times the concentration of sulfate ions. Do we need any exponents? No, because there are no coefficients. So what do we know about this? We know the 1.1 times 10 to the negative 10th for the KSP. We don't know the barium or we don't know the sulfate. That's what we're looking for. If this is a saturated solution, then all the solid that could dissolve does dissolve. So I get X amount of that. Every time I get X amount of that, I'll get X amount of that, because there's 1 for 1 whenever one of those dissolves. So then I could go over here and plug in X for the barium, plug in X for the sulfate, and that equals X squared. So how do I get the concentration of barium? Well, I solve for X by taking the square root. And so the square root of 1.1 times 10 to the negative 10th is 1.05 times 10 to the negative 5th. Now, that represents concentration of barium. That's molarity. And that is equal to the concentration of barium. What if it had asked me for the concentration of sulfate? That also equals the concentration of sulfate. But that's not what was asked in this problem, but still does. Okay, so we can solve for concentration. We can solve for KSP. Should we practice some more? Yeah, give us some more. So here's some more. What is the chromate ion concentration in a saturated solution of silver chromate if the KSP is 1.1 times 10 to the 12th? All right, so hopefully you're getting used to using a lot of dissolving equations. What do we get here? We get 2 silver ions dissolved and a chromate ion dissolved. Okay. What's the KSP for this? KSP is expression. The expression is going to be a concentration of silver ions times the concentration of chromate ions. But wait, are there any exponents? Yes, there's a coefficient of 2, so that becomes the exponent for the silver. What do we know about this? Well, we know this is going to be equal to 1.1 times 10 to the negative 12th. Now, let's figure out what we should plug in. If this is a saturated solution, then the most that can dissolve does. What does it dissolve from? The silver chromate is what it dissolves from. So every one of these that dissolves gives me 2 of these and 1 of those. What's easier to call X? This is easier to call X because there's no coefficients. So every time we get X chromates, we get 2X sulfates. Alright? So, oh, you guys hear the train? There's a train coming. So what I have to do is plug this in for silver and plug this in for chromate. So now I'm going to have 2X squared times X. And that gives me 4X squared times X, which is 4X cubed. So how do I solve for X? I just divide by 4. And now I have X cubed is equal to, I wrote this on another sheet of paper, 2.75 times 10 to the negative 13th. Then I got to take the cube root of both sides to get X. And I find out the cube root of 2.7 times 10 to the negative 13th is 6.5 times 10 to the negative 5th. What does that mean? That's X. What is X? X is the concentration of chromate So what's the concentration of chromate? 6.5 times 10 to the negative fifth molar. Right? Hey, what if I ask for the concentration of silver? Well, the concentration of silver is twice that, even though it doesn't ask for it. Concentration of silver is 2 times 6.5 times 10 to the negative fifth. Right? Molar. Yeah, keep that in mind. All right, so this time we're going to calculate the KSP in a 0.5 liter of saturated solution, knowing that 7.5 times 10 to the negative fourth grams of iron hydroxide is what dissolved to make that saturated. Okay, so hey, how about a dissolving equation? I'm so used to those. Iron hydroxide solid dissolves to make iron ions and hydroxide ions. All right, what do we know? Oh, we're trying to find KSP. So let's write the KSP expression. Take the iron ion concentration, multiply it by the hydroxide ion concentration, but wait, there's a coefficient of 2, so we got to square that. All right, so we know that 7.5 grams times 10 to the negative 4 saturated the solution. So this is how much iron hydroxide dissolved. So let's take that 7.5 times 10 to the negative 4th grams of FeOH2 and change it into moles. So we take 1 iron, 2 hydrogens, 2 oxygens, and we get 89.87 grams of iron hydroxide for every mole. Where'd I get that? You got it. Right. And we find out that there's 8.35 times 10 to the negative 6 moles of iron hydroxide in the solution. But wait, there's more. Okay, that's in 0.5 liters. So I need concentration because I need molarity to plug into these to get KSP. So I divide it by 0.5 and I find out that I get 1.67 times 10 to the negative fifth molar. Okay, what does that mean? Well, let's figure out what's X and what's 2X here or whatever. Okay, so if this dissolves, I'm going to get one of those, so let's call that X, and 2 of those, so let's call that 2X. All right, so what do we got to do now? Well, we got to plug X and 2X into, we got to figure out what X is. Well, here's how much iron hydroxide dissolved. Here's the volume. So this is the molarity of the iron ions, because you get 1 for 1, but it's 2 times, you got to plug in for X right there. Okay, so then what's the KSP going to equal? It's going to equal the 1.67 times 10 to the negative fifth molar for iron ions, and then 2 times 1.67 times 10 to the negative fifth molar for hydroxide, but we have to square that. And that gives us 1.86 times 10 to the negative 14th for the KSP for iron 2 hydroxide. It's a really small number because it's not very many ions that dissolve. Okay, so what have we learned today? Hopefully you know that in order to do a KSP, you're going to need a dissolving equation. Okay, when you dissolve it, break up those ions and put in the coefficients if you need them. Okay, remember to put the coefficients as the exponents when you're doing your KSP. Thanks, Boxing Hippo. You're the best. We love you. Yeah, love Boxing Hippo. Okay, so can you do this? Okay, that's an objective for the unit. Hope you can. Peace out from Harbin.